Hello, stats. This is a video for 3.2, conditional probability and the multiplication rule. I can find the probability of an event given that another event has occurred. And this we are going to call a conditional probability. Number two, how to distinguish between independent and dependent events. Number three, how to use the multiplication rule to find the probability of two events occurring in sequence and to find conditional probability. So conditional probability is the probability of an event that has occurred given that another event has already occurred. So to write a conditional probability, so just in general terms, a probability of A given B. So this vertical line right here is standing for given, which means that we have a conditional probability. So it's finding the probability of A given that something else has already happened. So example one, two cards are selected in sequence from a deck of cards. Find the probability that the second card is a queen given that the first card is a king. Assume that the king has not been replaced. So a little review on decks of cards. There's 52 cards. There's 13 of each suit. And there's 4 of each number. So aces all the way to kings, 4 of each of those. So if we take a king out and we assume that it's not replaced, we want to find what's the probability of getting a queen given that a king has already been picked. And so if a king's already been picked, that's going to change our sample space. So instead of having 52 cards in there, we now have 51. And of the 51 cards, 4 of them are queens. So we have 4 favorable outcomes, which equates to a probability of about 0.078. And so that would be an example of finding a conditional probability. So we're assuming that some other event has occurred, and we are going to find the probability after that event occurred. Secondly, we'll find some conditional probabilities from a chart, and this is called a two-way table. And two-way tables are used to organize categorical data. So you can see that the data that's collected is in words, yes and no, and then male and female, so this would be categorical data. So of these 2,276 social media users, they were asked if they've ever been offended by something they saw on social media. Find the probability that a user is male given that the user was offended by something on social media. So we're going to find the probability of a male given that they were offended. So our condition is that we're only going to focus on the offended. So we're only going to look at the sample space of the offended people. And so looking at my chart over here, have you ever been offended? So here are all the people that have said yes. So I'm only focusing on the people that have been offended, which is 1151. And of those 1151, how many are male? That would be 532, which ends up giving me a probability of about 0.462. Another one we could look at is what is the probability of not being offended given that the user was female. So we could check that one out. So let's take a look at that real quick. So now we're going to focus just on the sample space of female. So here's my condition. I'm only going to focus on this sample space. So here's my females. And how many of those were not offended? So that would be 549 over 1,168, which is going to give me a probability of about 0.470. So conditional probabilities are where we're assuming that one of the events has already occurred. So here we're only focusing in on the offended, or given that they're female, and then we can find the probability within that sample space. In each of our two examples, we were looking at different types of events. So independent events are events where the occurrence of one event does not affect the probability of the other, and then dependent events is where the occurrence of one does affect the other. And that would have been when we picked the king and we decided not to put it back in. So that changes the probability of getting the queen. So instead of getting a 4 out of 52 chance for the queen, we're now having a 4 out of 51 chance, which is going to affect the probability. So we're going to look at classifying the following multiple events as whether they're independent or dependent. So decide whether they're independent or dependent, selecting a king from the standard deck, not replacing it. So it's not replacing it, that's going to change the sample space. So that is going to change the probability of picking the queen. So this one is a dependent situation. Tossing a coin, getting a heads, and then rolling a 6-sided die and then getting a 6. So tossing a coin is not going to determine whether or not we get a certain number on the dice, so this is going to be independent. So the first event, tossing a coin, is not going to affect what the result is when we roll the dice. Number 3, driving over 85 miles per hour and then getting in a car accident. So the first event, driving 85 miles per hour, is probably affecting whether or not you get in a car accident. So this would be a dependent situation. So that is going to affect the car's mobility and give you a different chance of getting in an accident. So the 2 ways that we can find the probabilities for independent events and dependent events is first finding dependent events, the probability of A and B happening. It's the probability that A is happening times the probability of B given that A has already happened. So looking back at our king example, the probability of getting a king and a queen from 2 cards would be the probability of getting a king, 4 out of 52, times the probability of getting a queen, 4 out of 51. So we have a queen that has been taken, excuse me, a king that's been taken out, so now we have a different probability. And then independent events, probability of A and B, we simply just multiply the 2 probabilities together. So the probability of tossing a coin getting a heads and on a dice rolling a 6 would be 1/2 times 1/6. So the rolling of the dice is not going to be affected by the tossing of the coin. So we're going to look at those 2 examples again. I guess I just kind of did those, but 2 cards are selected without replacing the first card. What's the probability of selecting a king and then a queen? So probability of getting a king and a queen is going to be the probability of getting a king times the probability of getting a queen after we already picked a king. So getting a king, we had a 4 out of 52 chance, times getting a queen, we have a 4 out of 51. If we times those together, we end up with a probability of about 0.006. So if you're a poker player, getting a king and a queen, not a very good chance of just getting those 2 cards. Next, a coin is tossed and the dice is rolled. So what's the probability of getting a heads and then rolling a 6? So probability of heads. And 6 is the probability of getting a heads times probability of getting a 6, half times 6, which ends up being about 0.083 repeating, and that would be our probability of that happening. And you can kind of see as you're finding these probabilities of these independent and dependent events, you can see the counting principle at work. So the number of total outcomes, the 52 times 51, that would be using that counting principle, and that would end up being the total number of outcomes that could happen when you're dealing out these cards. And same with the rolling the heads, the rolling the dice, and tossing the coin. That would be the total outcomes, 12, that could happen in that situation. Getting through some statistical probabilities. So for ACL surgery, the probability that the surgery is successful is 95%. Find the probability that there are 3 successful ACL surgeries. The situation we're looking at is independent. So somebody getting an ACL surgery in Minnesota and seeing what their recovery is not going to affect somebody getting an ACL surgery in California and seeing what their success rate is. So these are independent events. So we're going to find the probability of a success and another success and a third success, which is going to equal the probability of S times the probability of success times the probability of success, which is 0.95 times 0.95 times 0.95. So the chances of 3 surgeries being successful is about 85.7%. Find the probability that 3 ACL surgeries are not successful. So the probability of failure, failure, failure is going to be the probability of F times the probability of F times the probability of F, which is 0.05 times 0.05 times 0.05, which is going to end up being about 0.001. And then lastly, find the probability that at least one of these 3 surgeries is successful. So we're going to find the probability that at least one. So that could mean that one of the surgeries is successful out of those 3, 2 of them are successful, or all 3 of them. So the total sample space is always going to add up to 100%. So the total possible probabilities add up to 100%. And if we want to find the probability that at least one is successful, then we can think of it as, well, what is the probability of the surgery, the 3 surgeries not being successful? So all 3 are not successful. That's the only probability that would mean that at least one wasn't successful. So a little probability trick, when we're looking for the probability of something at least one, it is all of our probability, 1, so 100%, minus the probability of none. So in this case, the probability that we have at least one success is going to equal 1 minus the probability that we have 3 failures. Well, that's the only way that we cannot get at least one success. And up above here, we have the probability of a failure. So 1 minus 0.001, or I should say 3 failures. So the probability of getting at least one successful surgery would be 99.9%. So at least one out of those 3 would mean we'd have a 99% probability. So lastly, some more statistical probability. In a recent year, there were 18,187 U.S. medical school seniors who applied to residency programs and submitted their residency program choices. Of these seniors, 17,057 were matched with residence positions. So our probability of getting a match, which I'm going to call M, is 17,057 over 18,187, which results in about 93.8%. So of those seniors, 17,057 were matched with residency positions, with about 79.2 getting one of their top 3 choices. So the probability of somebody getting a top 3 choice, given that they were matched, is 0.792. So it goes on to say that students will pick their top 3, and then if the school picks them, they will match each other. And that's where the preference list of the school matches the preference list of the student, and that's how they get matched to that top 3 placement. So we're going to find the probability that a randomly selected senior was matched with a residency position, and it was one of the senior's top 3 choices. So this would be the probability that they were matched and it ended up being top 3. So the statistic that we have, the 79.2%, is a conditional probability that they did get matched and got that top three. So to find this probability, we'll take the probability of a match times the probability that they were top three, given that they had a match. And so that would be 0.938 times 0.792, which gives us a probability of about 0.743. So getting in that top three was dependent on whether or not they were matched. So that was a dependent probability. Find the probability that a randomly selected senior was matched to a residency position, did not get matched with one of the senior's top three choices. So given that they were matched, they did not get in their top three. So this would be the probability that we have the complement of top three, given that they were matched. And so the probability that they were top three, given that they were a match, was at 79.2%. So the rest of the percent did not get their top three. So we would do 1 minus 0.792, which gives us 0.208. And then lastly, would it be unusual for a randomly selected senior to be matched with a residency position? We'll continue looking at this idea of unusual. And unusual is when a probability is below 5%. So we'll keep keeping that in mind, that anytime we have a statistical probability that's lower than 5%, then that starts to be a little bit unusual. Well, we just found a probability that they don't get matched to their top three is going to be a 0.208. So 20.8% is greater than 5%. So this is not unusual. This is a pretty common occurrence. So that wraps up our 3.2 notes looking at multiple probabilities, identifying independent, dependent events, and then finding some statistical probabilities.